Hello there. Let's look at Bohr model. And in order to look at this one, we want to think about the Rutherford's model. And that one shows the protons in the center, the nucleus, and it's positively charged. And the electrons are sort of scattered around, right? And it's a fuzzy picture, not clear. And also he was puzzled by not knowing what is a neutron. And later in the 1930s, Chadwick explained neutrons, and also he explained isotopes. That gave a good picture, good idea for Bohr to come up with this planetary model. What's that? The nucleus is like the sun, and these electrons are in the shells are more like the planets, the Mars and the Earth orbiting around. So that's the idea. But we know the electrons have maximum numbers 2, 8, 8 and so on for each shell. And that's also important to when you look at the um, periods, right? So look at the progress, right? So the planetary model, Sun and the Earth and Mars and other things is orbiting around and defined shells and relationship to the periods. The periods we know in the periodic table goes from 1 to 7. And actually the energy levels, the quantized ones also go from 1 to 7 and we label them K, L, M, N, O, P and so on, right? Now, so these energy levels also we put a simple n and then it very end it goes to the infinite, right? Now, by looking at the atom, you see what we see here is actually from center of the nucleus to the bottom. So it doesn't really make sense when you go down because energy is going up. The better one is I put the I there from center of the nucleus to the look up. So that's what we want to do. So that way it will give you a better idea. Let's look at that way. Here is nucleus is in the bottom of the screen and halfway up we are looking now. So these are the N, the energy, principal energy levels. So energy shells, main energy levels. These are 1 to 7. And if you go further and further and further, you're going to end up with infinite. That's the ionization actually, right? So if you kick out an electron all the way beyond the atom, that's ionization. Now, when the electron is sitting in the bottom, it's called the ground state. And this one is for the hydrogen atom. Anything in between, anything off of the ground state is called the excited state. Now, in the ground state, this electron, actually, if you sap with some energy, some light, let's say 3 joules, and it will jump up somewhere. Let's say it lands on the 4th level, exactly on the 4th level. And it absorbed 3 joules and jumped up to the 4th level. Now it's going to relax. It's going to come down. When it comes down, it's going to offload exactly the 3 joules of the same light energy. So that's the emission. So that we have to understand that. So nothing is kept and it's taken and given back later. Now, I can sort of show this one as a transition. There are a bunch of transitions we want to know. And these transitions are, we can say, you see, if it comes to the first energy level, that's called the Lyman, the UV series. And then this, if it comes to the second level, it's called the Balmer, the visible series. And then the beyond that is, I call the PBS. See the P for the Partian, BS for the bracket series. And these are IR, they're very little amount of energy. So to be aware of the electromagnetic radiation, I will discuss this one in a different video. But that's important. Now, there's another important thing. Look at this side stairwell. This is like a guy on dope fixed the stairwell. It's not equal. But what's more important, see, it represents the each 1, 2, 3. If you're jumping up with the electrons, it needs to get energy, absorbs energy. That's called the absorption spectrum. Now, if the electrons are jumping from top to the down, and that's the release of energy, that's the minus delta E, that's the emission spectrum. So this is more like the stairwell unusual one, and there's a frog jumping up and down. There's no specific defined location. It can go 2 to 3, 4 to 5, 1 to 3, whatever, right? Now, let's look at how we do the math on these ones. So your energy, the transitions of an electron is an initial energy level 2, 2, 3, 4, whatever. right? So that can be written as delta E is E final minus E initial. That's only delta E. So make sure you're calculating delta E, change of energy. That's given by minus 2.18 10 to the minus 18. That's the Rydberg constant, and the 1 over n final squared. And then if you're using hydrogen, it's normal one. If you're using anything else, the c squared should be there. Okay, but the most useful one is the blue cage one, and this is for a electron proton atom, one particle, and also it could be for helium plus, lithium plus 2, beryllium plus 3, boron plus 4, and so on. So make sure it's a monoelectronic system and hydrogen like system in order to use this one particle formula to calculate the delta E, right? We also need c is equal to h nu. That's for the velocity of light, the wave number, and the frequency. And you can play around with that one. You can actually plug into the E is h nu, and the nu is c over lambda. So these two, c is lambda nu and E is hc lambda, is really important to do the math. Okay, now the general idea again, just think about the Rutherford Chadwick's moving into the Bohr's planetary model, and then we kind of want to link to the periods to the energy levels. Okay, now it's kind of upside down, so try to understand what's the better way to look at from the midpoint to upward. So to understand the ionization, to understand the ground state, understand the excited states. You got the point? So okay, transitions. Now emission and absorption spectra. We can talk about that, thinking about the stairwell, unusual, but there's no in between steps stopping, but only each level somewhere up or down you can go, right? Okay, now let's have fun here. Calculate and prove the hydrogen first ionization energies given in the data books are 1312 kilojoules per mole. Let's see if we can calculate that. This is what you do. You take the normal formula, Rydberg constant, and then 1 over alpha squared and 1 over 1 squared, because your electron from the first level and kicked out to the infinite. That's why the final is infinite squared. So you plug in, then 1 squared is 1, and then you get 2.18 10 to the minus 18 joules. I don't see the 1312. What do? This is for one atom. So Avogadro number of 1 mole is that much, and 1000 joule is kilojoule. So the cancel the mole to mole, joule to joule, you get kilojoules per mole.